In our last episode, we told the story of the FGF family FGF1, FGF21, and FGF19, and how each of these molecules acts on the hypothalamus to influence appetite, insulin sensitivity, and glucose metabolism. We saw that FGF1 fits the theory perfectly, but carries cancer risk. FGF21 and FGF19 are safer natural alternatives already in clinical trials. But here's the central question that emerged from that story. How do we effectively stimulate the hypothalamus to achieve these metabolic benefits? What if the answer lies not in a single molecule, but in an ancient communication system already built into our bodies? In this episode, we introduce a compelling theory that the immune system, through its natural signaling pathways, can be harnessed to stimulate the hypothalamus and improve type 2 diabetes. Let's explore the evidence. The anatomical and functional basis for this crosstalk is well established. Circumventricular organs, CVOs, such as the median eminence, possess a leaky blood-brain barrier, permitting circulating cytokines to access hypothalamic nuclei. Pro-inflammatory cytokines, particularly interleukin-1 beta, interleukin-6, and TNF-α activate NF-kappa B and JNK signaling in PVN corticotropin-releasing hormone, CRH neurons, triggering the HPA axis. This is not an artificial construct. It is a physiologically conserved neuro-immune circuit that operates under both homeostatic and pathological conditions. Clinical evidence supports a pathogenic link. Type 2 diabetes is associated with chronic HPA axis hyperactivity, manifesting as elevated circulating cortisol and ACTH levels. In a study of type 2 diabetes patients, morning cortisol levels showed positive correlations with fasting plasma glucose, HbA1c, and body mass index, indicating that HPA axis dysregulation correlates with the degree of glycemic control and metabolic dysfunction. Mechanistically, this may reflect glucocorticoid receptor resistance, a phenomenon where elevated cortisol fails to exert negative feedback, perpetuating hyperglycemia and inflammation. Direct experimental evidence comes from a landmark 2025 Nature Communications study. The authors identified a resident population of regulatory T cells, Tregs, within the mouse hypothalamus, particularly in the arcuate and paraventricular nuclei. Under high-fat, high-sugar diet feeding, these Tregs declined, coinciding with local microglial activation and insulin resistance. Critically, Treg gain-of-function experiments through adoptive transfer or pharmacological expansion reversed the metabolic phenotype, improving glucose tolerance and restoring hypothalamic insulin sensitivity. This provides proof of concept that targeted immune modulation within the hypothalamus is sufficient to correct type 2 diabetes-related metabolic defects. Based on this evidence, we propose a testable hypothesis. 1. Peripheral route. Administering a controlled immune stimulus triggers a cytokine response that is sensed by the hypothalamus via CVOs, leading to HPA axis activation. Given that cytokines such as interleukin-6 and TNF-α are known to modulate hypothalamic insulin and leptin signaling, this pathway may enhance peripheral insulin sensitivity. 2. Central route. Alternatively, engineering immune cells to home to the hypothalamus and locally modulate neuroinflammation, for instance. By expanding Tregs or modulating CCR5, CCL5 signaling in the arcuate nucleus may achieve a more targeted effect, with fewer systemic side effects. In both scenarios, the key mechanistic output is the restoration of hypothalamic insulin and leptin signaling, which in turn reduces hepatic gluconeogenesis and promotes glucose uptake. In summary, the neuro-immune interface, particularly the cytokine to HPA axis pathway, represents a biologically plausible target for metabolic intervention. Our hypothesis is grounded in established mechanisms and supported by direct experimental evidence, including the demonstration that Tregs in the hypothalamus can control local immune activation and reverse metabolic impairments. Critical questions remain. What is the optimal immune stimulus? Is the effect dose and timing dependent? Does it generalize from rodent models to humans? We are now designing preclinical studies to test these parameters. The answer may redefine how we approach type 2 diabetes therapy. This is Dr. Yang's Health Tips. Thanks for watching.